All right, I've set up a half Atwood machine with a 0.6 kilogram mass up on the table with some static coefficient of friction, 0.333, and a 0.1 kilogram mass hanging off of the string. And I want to see if I can figure out the max friction force first. So that is force friction has to be less than or equal to mu static times force normal. So then the max value is mu static times force normal. So let's think about what M1 is doing. M1 feels force of gravity, M1 G. M1 is touching the table, so it feels the normal force. M1 is feeling some friction force. And M1 is pulled by a force of tension. So that means that in the y direction, I have force normal equals M1G equals 0.6 times 9.8. And then up here, I can just go 0.333 times 0.6 times 9.8. And I find out that my max friction is just 1.96 newtons. So now let's figure out the system equation. So with the system equation, we're looking at external forces. That is this one, M2G, and this force here, force of friction. So my system equation is going to be M2G minus force friction is equal to M total A. I have a force that is in the direction of motion. If this thing moves, it's going to move in the direction of M2G. I have a force that is against the direction of motion, that's negative, and then the total mass gets multiplied by the acceleration on the other side of my equation. So in this equation, I can figure out M2G, that is 0.98. And let's take a look at this. 0.98 minus to 1.96 is equal to M total A. So when we think about static friction, you have to remember that the static friction maximum is that number we calculate by mu times the normal force, but the actual force is only as strong as it needs to be. So let's just keep calling it force of friction, and let's call this 0. So now we have 0.98 minus force friction equals 0. And that tells us that force friction is equal to 0.98. So then we can say Is this less than the max allowed? Yes. The system is actually static. So if you set this thing up and release it from rest with 0.6 kilograms up here and 0.1 kilograms down here, the pulling force is not strong enough to overcome the friction force. So let's real quick do it again with a heavier hanging mass. So we'll keep the same M1 as 0.6 kilograms, and mu is equal to 0.333, but now we'll make M2 is equal to 0.3 kilograms. So we'll still have the same max force of friction is equal to 1.96, but now we'll go ahead and check M2G is 0.3 times 9.8 is 2.94. So if static, then M2G minus FF equals 0. So 2.94 minus FF equals 0, which means FF equals 2.94. And then we look at that and say, no, it is not allowed to be 2.94. It's only allowed to be 1.96. So that's how we know the system is kinetic. So then we do kinetic force friction is equal to mu kinetic times force normal. I didn't give a different mu kinetic, so without a different value, we just assume it's the same thing. So that's 0.333 times 0.3 times 9.8 is equal to 1.96. And then we have M2G minus force friction is equal to M total A. And this is our 2.94 minus this is our 1.96 equals total mass 0.9, 0.3 and 0.6 is 0.9 times A. So that's how we can figure out 2.94 minus 1.96, close parentheses, divided by 0.9. The acceleration is 1.09 meters per second squared is equal to A. And then the one other thing I wanted to talk about here is the tension in the rope. So to deal with the tension in the rope, we have to think about M2, and it's M2G, and it's force tension. And let's go back to static with M2 equals 0.1. Then we'd have force tension minus 0.1 times 9.8 equals 0. So force tension is equal to 0.98. In kinetic, M2 was equal to 0.3. Hang on, I made a mistake up here. This was 0.6. Sorry, that's corrected now. I copied the result, but I wrote the wrong work up here. And A equals negative 1.09 meters per second. So up here, this is the magnitude of the system acceleration. This is component of object. It's the y component acceleration. So then we have force tension minus 0.3 times 9.8 is equal to 0.3, just a single object, times negative 1.09. So force tension is equal to 0.3 times 9.8. That gets added over to the right-hand side, minus 0.3 times 1.09. And we get 2.613. 2.61 newtons. And note that that is less than the M2G, which was 2.94, because our object is accelerating downwards. So when you're accelerating in the negative direction, you require less tension to hold on to the object. So there's a full pair of half Atwood's machines analyses for you.